Welcome back. By now you've learned a sound reinforcement system is an electrical system made up of many smaller electrical systems and circuits. Therefore, it's prone to all the problems any electrical system can have, notably hums and buzzes. In this section, we're going to talk about the most common electrical problems sound engineers deal with and some things you can do to solve them. With the mains turned off, hums and buzzes on stage may be nearly inaudible, but when the mains come up, the noise will become greatly magnified due to the multiple gain stages in the system. So, one of the basic responsibilities of the sound engineer is to make sure the system is effectively grounded and that system noise is eliminated as much as possible. Fortunately, most of the grounding and system noise problems you'll encounter can be solved with the right tools and an understanding of how to go about isolating and solving the problem. To give you a fundamental understanding of what some of the important issues are, let's go to a final edition of Sound School. System noise is the term we use to describe the unwanted hums or buzzes in our PA system. The biggest source of system noise comes from ground loops, and ground loops typically come from improper system grounding. Interestingly though, the very thing that's used to keep a system safe is also the culprit behind a lot of the system noise, grounding. So when we say proper system grounding can go a long way towards solving typical system noise, we're not just talking about making sure all the plugs are pushed into the wall sockets. Let's talk first about what grounding is. Grounding is the directing of the flow of electric current safely down to earth where it's dissipated. The primary reason we do this is to prevent the electric current from taking a course to ground through our bodies and exposing us to electric shock. It's very important to understand that electrical problems aren't just annoying. A sound system, even a smaller system, can produce enough current capable of seriously injuring or even killing someone if not properly grounded. In a sound system where there may be dozens of electrical devices, each with their own AC plug seeking ground, the very noise we want to eliminate often comes as a result of too many paths to ground. When there are too many paths to ground, loops can be created within the grounding paths, which act like antennas. These loops pick up the surrounding electromagnetic field, and rather than draining it off directly, recirculate it through the system to be amplified along with everything else we're amplifying. To reduce system noise, there are 4 areas we need to focus on: AC power outlet considerations, using the correct audio system cabling, understanding how and where to interrupt the shield ground, and understanding the various connectors used within an audio system. Ideally, you want to have 1 or more 20-amp circuits just for the sound system. It's always worth trying to find this information out from the club manager or building electrician. Also, it pays to have an idea of what the power needs are for the system you're using. The formula for this is watts divided by volts equals amps. Add up the total watts of your power amps and divide by 120 for volts. The resulting figure is the amperage your system draws at peak load. You should always check the outlets you plan to use for the system. Purchase a multimeter, which you can use to test AC outlets for correct voltage output as well as cable continuity. If a fault is detected, the outlet should not be used. Try to spread your power among several outlets on the same circuit instead of overloading one outlet box. If you're experiencing ground loops, never use an AC ground lift like this to lift the entire system. Instead, use balanced lines and cables with 3-prong AC plugs without adapters, and interrupt any ground loops at the line level shield grounds, which we'll talk more about in a moment. In audio systems, there are primarily 4 types of cabling: microphone cabling, line cabling, power cabling, and speaker cable. For all types of cabling, there are 2 important things to remember. First, use the correct type of cabling for each application. And secondly, the cable you use must be adequate to handle the necessary amount of current for a given application. Microphone cables carry the audio signal to its destination in either 2 basic ways. Unbalanced cables use one of the signal-carrying conductors as a shield against electromagnetic interference. Balanced cables use matched signal-carrying conductors with a 3rd conductor surrounding it as a shield. Although unbalanced mic cables are cheaper and reasonably effective over short distances, there are 2 disadvantages. First, unbalanced mic lines are typically terminated into extremely high impedance, and the higher the impedance, the more susceptible to electrostatic interference. If you've ever turned on a fluorescent light and heard the buzz it produces, you've heard electrostatic interference. Like fluorescent lights, electrostatic interference can manifest itself as an audible buzz in the output sound. The second disadvantage with unbalanced cables is the longer they are, the more noticeable the deterioration of high-frequency response becomes. This can be compounded by the high-frequency buzz to which this cable is already susceptible. Balanced cable, on the other hand, has a lower impedance than unbalanced cable, and it's designed to allow the shield to drain electrostatically induced currents independently off the signal-carrying conductors. An even more significant advantage is that electromagnetic fields, which are not deterred by a shield in the cable, encounter identical conductors that are twisted into a spiral inside the shield. The twisting causes the electromagnetic field to be continually reversed with each full twist, largely preventing its influence from traveling along with the mic signal. In the unbalanced cable, the conductors are of different configurations and thus have different electrical properties than one another. As a result, they're unable to cancel out electromagnetic interference. Another advantage of balanced circuits is that they readily allow the shield ground to be disconnected or lifted at one end in order to avoid ground loops. The bottom line? Always use balanced low impedance lines for your microphone cables. Direct input boxes are another source of potential grounding problems. Generally, when a DI box is used to connect a grounded musical instrument amplifier to the snake using a balanced XLR type mic cable, the ground lift switch needs to be in the lift or off position. Such a switch is designed to disconnect pin 1 of the XLR connector on the unit. If the amplifier uses a 2-prong AC plug, leave the switch on the DI in the ground or on position. The next type of cabling is line level cabling, such as cables used to connect instruments to amplifiers or cables used to connect system devices to the mixer, such as effects or dynamics. Here again, whenever possible, use balanced cables. Balanced cables provide the maximum flexibility for arranging an effective grounding scheme. Next is power extension cabling. Always use shielded, heavy-duty, grounded 3-prong AC power extension cable to extend a power line if you're limited in available circuits and need to draw as much amperage as possible. Our final cable type is speaker-level wiring. This is the only cable type where shielding is not necessary or helpful. Normally we use simple 2-conductor cables. The diameter of speaker wire is given a numeric gauge number. The smaller the wire, the higher the gauge number. For example, a number 4 gauge wire is larger in diameter than a number 16 gauge wire. The diameter is important because the smaller the size of the speaker cable, the greater the impedance or resistance of the cable to the flow of current. As the resistance increases, so does the rate of power loss. For a moderate-sized system, we recommend a speaker wire gauge of at least number 16 or lower. As we mentioned earlier, too many paths to ground from all the various devices in an audio system can be a big contributor to system noise. The solution for this is to use balanced cable throughout the system and interrupt the shield ground at certain points. Let's look closer at how this works. In every cable, connector, and electrical device used in an audio system, there's a grounding capability. In a cable, it's the shield. In a connector, it's the sleeve or a pin. In a device, it's the chassis ground. The purpose here is to maintain the flow of ground throughout the system until it can safely be carried, ultimately, to Earth through the 3rd prong of a 3-prong AC plug. So how does this flow occur? Basically, from the shield ground inside the cable, through the connector, to a shield ground connected to the chassis of an electrical device, then a ground from the chassis to the 3rd pin of the AC plug for connectivity to Earth. It's in this manner that ground is passed through from device to device. Ground loops form because of the proximity and continuity between other system grounds. So it's important to understand where to interrupt the shield ground so that ground loops can be avoided. You don't interrupt the chassis ground. That would make the device ungrounded and a shock hazard. Instead, we use modified cables and connectors with the shield already lifted in certain places in the system. Here's how to lift an XLR on a balanced cable. On the female XLR end of a balanced cable, open up the connector and unsolder the shield from pin number 1. Insulate the exposed shield end with electrician's tape to ensure contact is not accidentally made within the connector. After reassembling the connector, be sure to color code it to show it's a modified cable. Another method is to purchase modified shunt adapters, which have the ground wire already lifted from pin 1. You can then simply connect the adapter to the female XLR connector on the cable you need lifted. There are several systems on the market which provide isolation transformers with ground lift switches. Here's the Proco IT8A, which provides 8 channels of isolation transformers with ground lift switches. A device of this type would eliminate the need for lifting the shield ground on the cable itself. As a sound engineer, you need to be familiar with a variety of adapters and connectors, so let's go over several typical ones. This is a balanced low impedance to unbalanced high impedance transformer adapter. This type of adapter allows you to connect a high impedance cable to a balanced low impedance cable. For example, an acoustic guitar with an internal pickup could be easily adapted to a mic cable. This is a double female 1/4-inch phone jack which allows 2 1/4-inch plugs to be connected. Here's a female phone jack to male phono plug for tape deck inputs or outputs. The phone plug is also known as an RCA plug. This adapter is the reverse of that, a female phone plug to a male 1/4-inch phone plug. This is an RCA Y cord. It allows tape deck outputs or inputs to be joined with a single mixer input or output. This is a dual banana plug used to connect a power amp to whatever configuration is being used for speaker wiring. This is useful if you need to adapt a spare power amp on the spot. Here's a female to 2 male XLR Y cord. This allows 1 cord to feed 2 units when necessary. Here's the opposite, a male to 2 female XLR Y cord. Although you'd prefer to use a transformer isolated splitter or combining box, this type of cable could be used in a pinch to connect 2 mics to 1 input, such as using 2 SM57s to mic 2 toms. If you don't have a pad switch on your mixer, this mic pad adapter could come in handy. They're manufactured in a variety of attenuations. These adapters are called turnaround adapters. They're pre-wired to provide a simple turnaround when snake channels are wired in the opposite direction than what you may need. This is a common problem with crossover outputs and other signals headed back to the stage. This is a male and female XLR to male 1/4-inch plug, and this is the opposite, an XLR to female 1/4-inch phone jack. These adapters should be in every sound engineer's toolkit. Okay, school's out. Welcome back. As you've seen, keeping a system noise-free is an ongoing job for a sound engineer, especially since moving the system around always seems to introduce a variety of new problems. Hopefully, this section on electrical problems has helped by giving you an idea of what causes problems in the first place and what you can do to deal with them. Let's briefly summarize what we learned in this section. When it comes to grounding, there are 4 areas of consideration. The first is the AC power outlets. Determine the power demands for your system by adding the total wattage from your amps and dividing by 120. The resulting figure is the amps necessary to power your system under peak load, and will give you a rough idea of how many circuits should be set aside. Buy a multimeter and use it to check the outlets on the circuits you'll be using. If a fault is found, don't use that outlet. Always use 3-prong AC plugs without adapters to plug into. The second area of consideration is the cabling used in the audio system. For mic cables, use balanced low impedance lines. With a direct box, the ground lift switch needs to be in the lift or off position when it's used to connect a grounded musical instrument to a snake using a balanced XLR type mic cable. If the stage amplifier uses only a 2-prong AC plug, generally leave the DI switch in the ground or on position. For line level cable, use shielded low impedance cable. For power extension cable, use 12-gauge shielded extension cable. For speaker cable, you can use number 16 gauge or lower unshielded speaker wire. The third area of consideration is safely interrupting the shield ground on a cable connector or shunt. Review the process for modifying a connector earlier in this segment. The fourth area of consideration is understanding the various audio connectors used in a sound system and being familiar with their usage. Having the right adapter at the right time can solve a problem that occurs when you least expect it. Besides a variety of connectors and adapters, a sound engineer's toolkit should include a multimeter to test wall outlets and cable continuity. A soldering kit is essential, as well as a variety of electrical tools. It's always better to be prepared. In sound reinforcement, electricity can be as much an enemy as it is an ally. In this section, however, we've shown you some ways you can protect your system as well as the musicians in the band. For the next and last segment of part 1 of this program, we're going to talk about the actual mixing process. As a mixer, the engineer can not only play an important role in how the band sounds, but can also provide musical support and backup. We'll show you how when we come back for the final segment of part 1 of Live Sound Reinforcement.